All right, welcome everyone. So this is our 12th live stream geometry session. We have two people here with us now, and as usual, more usually join later. And today I chose problems from the Baltic Way math contest. So that is a competition. It originally started with Estonia, Latvia, and Lithuania, but then they added more teams later on. Iceland also participates. Germany has a team that participates. So it's a smaller group of countries, and they each send 5 students, and it's a team contest, which is kind of fun. So it's all 5 members of the team work together to solve 20 problems, and the whole team gets an award, but I don't think any individual students get awards. So it's kind of fun. All right, so with that, I'm going to jump into the problems. So let me share my screen. Just a second. I believe this should be it. All right, can you guys see it?
Yes.
All right. So let me maximize. Okay, so this, well, I think like half the problems I chose were from 2020, so pretty recent. I forgot to LaTeX them. Oh well. So ABC is a triangle with circumcircle omega. Hey, I3435, thanks for joining. So I chose all the problems from the Baltic Way math contest. So I was just mentioning that it's a contest. It started out with Estonia, Latvia, and Lithuania, but then they added a few more states. But it's a team contest. So it's like each country sends 5 students, and they all collectively work together on 20 problems. So it seems kind of fun. So we have triangle ABC. Omega is a circumcircle. Then we draw the tangent line at point A. Let's see. Where's my tangent? There we go. X and Y are the projections of B onto line L and AC. H is the orthocenter of triangle BXY. That's X. That's Y. And then I think orthocenter is triangle center 4. So let me clean up a little bit here. Okay. So then we have H equals triangle center. There we go. That's the orthocenter. We want to show BA bisects angle CB. Oh, first I have to define B. So CH intersects the line at D. Let me do this. Whoops, I didn't mean to. All right, we want to show BA bisects CBD. All right. Hold on just a sec. I see someone put something in the chat. And Rodrigo's on. Hey, Rodrigo.
Hi, Michael. Hi, everyone. Nice to join you.
Thanks. Is it Brazil? They didn't have daylight savings time, right?
I'm sorry. What have you said?
Oh, so in the U.S. they set their clocks back an hour.
Yes.
So is this an hour earlier for you?
Yeah, just an hour earlier. Yeah, not a big deal.
All right, sounds good. All right, so let's see. Looks like a good diagram. Okay, so maybe I'll just label those right angles. Why not? Two right angles. Obviously, BXAY is cyclic. So let's see. That's interesting. CH. Yeah, maybe I should draw in some of the altitudes. Maybe at least those two perpendiculars. I don't know. Yeah, because those two lines are parallel to AC and AD. So that would be good to draw in those two. All right. So YE is parallel to AD. XF is parallel to AC. We have a parallelogram here. Interesting. So, yeah, we could draw, we know BXAY is cyclic. So basically, we kind of want to show angle DBX plus ABX is CBY plus ABY. Is that just an angle chase? It might be. They're parallel, so YE is perpendicular to XB because since H is the orthocenter, it's intersection of the altitudes of this triangle. So YE is perpendicular to BX, but AB is also perpendicular to BX. So yeah, so AD and YE are parallel, and similarly AC and okay. So what if is there some way to angle chase DBX plus ABX? So ABX is 90 minus BAX, which is 90 minus BCA, which is okay. So XBA is equal to YBC. So we just have to prove that DBX equals ABY. Maybe that's also C. Yeah, maybe it is similar triangles in some way, because yeah, BA squared is the power of D with respect to this circle, and BX times BA is the power with respect to the other circle. Let's see. So basically, we want to show, like, I wonder if you could just use like spiral similarities. Yeah, basically, oh, yeah, I think I've solved it. Hold on just a second. Actually, now I'm not sure. So like we could try to show triangle BXY is similar to BDA. That would solve it. And we know one of the angles is equal. Let's see. A is the reflection of H in the midpoint of AX. Or the midpoint of AH, you mean, yeah. So yeah, this is a parallelogram. So yeah, A is the reflection of H in the midpoint of XY. Is that enough to prove that, I know I'm kind of jumping ahead a little bit here. Yeah, I'll just draw that midpoint just for the heck of it. Why not? So I mean, so yeah, another way to say it is that if we draw the circumcircle of BAD, we want to show CA as tangent to it. It's another way to frame it. See who else we can.
So I found that XY is tangent to the circumcircle of BYC.
So if I draw the circumcircle of BYC, you said?
Yes, the circumcircle of BYC is tangent to XY.
Interesting. Okay. So yeah, that makes sense because we have that angle is equal to that angle, which is equal to that angle. Interesting. Let's see. Oh, do these lines concur like on the circle? I think they do. Yeah, maybe if we show that that's a concurrence, it solves the problem. But that might be just as hard as solving the original problem. And I don't even know if it does end up solving the problem. Let's see. I wonder if YE passes through that point. Yeah. You just check it. But yeah, YE passes through that point, it looks like. And that's equivalent to what we're trying to prove, actually. Let's see. If the foot from C to AB is Z, hold on just a sec. The Z is on YE. All right, so I'm going to take your suggestion. If the foot from C to AB is Z, yeah, so it will lie on that circle. Also, YZ is parallel to L. By that well-known property. Okay, so basically, this point right here is the foot from C to AB. Yes. Okay, I could call that Z. All right. Feel like we're very close here. So then angle ZBY is angle ZCY. I feel like an angle chase here solves it, which is 180 minus angle A. Which is 90 minus angle A. Hold on just a sec. So is this angle and this angle is oh, but that's equivalent to what we want to show. Yeah. We want to show this angle equals angle A. Seems like BZ equals BX. Let's see. Yes. Yeah, there's so much going on here. It feels like it has to. Let's see. Yeah, if we can show this angle as angle A, that would solve it. Or in other words, if we could show this triangle is similar to triangle ABC, that would solve it. If T is the orthocenter, we need to prove that BDX is congruent to BTZ. If T is the orthocenter of what? Of ABC? Ah. Let's think about this. So, well, the reflection of the orthocenter over every side lies on the circumcircle. So, yeah, there's a lot of equivalencies here. Z is the midpoint of HY. Are you, I don't think so. Whoops. No, Z is not necessarily the midpoint of HY. I feel like we're
So
close.
are you trying to prove that YE passes through the point which intersects BD?
Yeah, if I can prove that, that would solve the problem. If I can show YE passes through that point. You know what? I'm thinking I might. I think I might have a solution. Hold on one sec. I think I can show triangle BXY is similar to triangle ABC. I don't know if that's enough. Oh no, I want to show BDA is similar to ABC, and I can show BXY is similar to ABC. Maybe we could use like the gliding principle. I guess if we could show cy over ya is ax over xd. Oh, so I think actually it might be the same as showing dxyc is cyclic. Let me check that. No. There's a lot of equivalencies here. I wonder if xf, let's see. Yeah, there's so many different, like, maybe we could show xf passes through this point. Let's see. Yeah, I'm trying to go for similar triangles here. Can we do stuff with ratios? Let's see.
So I think I can prove that XE passes through that point. XF.
Oh yeah.
Because XF is parallel to AY and angle, and if you assume that if you think that XF passes meets the circle at some point Y or Z, then
Okay.
Angle XIB will be equal to angle ACB because they're parallel.
I see. So I mean, I guess another way to think about it is angle AXB is 90 degrees, so angle AIB is 90. So I is the foot of the perpendicular. So
they lie on the circle.
All right, that is a good idea. Whoops. All right. I feel like we have to be very close here. So I want to show, let's see. Let's see. Yeah, at some point I need angle DBX. Or angle XDB. So the reflection, so HF has to equal FI because the reflection of the orthocenter over a side lies on a circumcircle. So HF is equal to FI. Wonder if we can use that fact.
Sir, the way we have proved that E, H, Z, Y are collinear, similarly going for the other side like Y, Z, H, E, and the last point on the side. Yeah, this one.
Yeah, if we can show it passes through that, that would solve the problem. I don't know if
Yeah,
there's like
it passes through that.
it. How do you prove that it passes through that point?
I think that follows from Siva theorem or something like that on triangle X, Y, B because we have proved the same for the other two sides.
Yeah, we proved XF passes through this point. Is the problem symmetric? Like, would it be the same argument? I'm
Mm,
not sure. Let's see. Uh, let's see. So, yeah, I'm wondering if we can like use the gliding principle. Hold on just a sec. So if we take the midpoints of AC and AD, then yeah, so I think LG and M are collinear. Yeah, we can prove that. Oh no, I can't. If we can prove that, I think that would solve it. I don't know if that does much. Wait a sec. I think we can prove that. I'm gonna take that away for just a second. But yeah, if I can.
What if we let that point D disappear for a moment and define D as the intersection of CH and AX and BK? Then try proving that these three lines are concurrent.
H, AH, and
AX and BK.
AX, BK. So this point D, right?
This seems controllable using some radical axis because there are many circles present.
Okay, so you're saying since these three lines concur, DB, DC, and DA, maybe we can use the radical axis theorem somehow, is what you're thinking. It's an interesting idea. One sec, I'll be right back, guys. All right, thanks everyone for waiting. Let's see. How do we finish this off? Yeah, I feel like we want to use that the reflection of H over G is A. It's just a matter of how we use that. Is X? Yeah, I think, yeah, XDH is similar to XYC. I think that might be the trick. So XD over DH is YH over HC, which is the same as AX. Yeah, I think we were making this harder than it has to be. I think it's actually very simple. Yeah. No, we're not out of ideas. I think I figured it out. Hold on just a second. So basically, it's not hard to show that dx over xa is ay over yc, because dx over xa is just dh over hc, and similarly with ay over yc. And so that really should solve the problem. So I'm going to write it up. But yeah, I'd like to see your idea. So yeah, maybe post it on the Discord channel, because I always like to see cool solutions like that. Let's see, just making room. Okay, so first of all, it's easy to show angle YBC is equal to angle XBA. So I'm gonna do that right now. So we have angle YBC is 90 minus angle ACB, which is 90 minus angle XAB, which is equal to angle XBA. All right. And so, yeah, let me delete some of the other stuff. Yeah, I've added a couple points. Maybe I'll delete them later. But once we know that, that means triangle YBC is similar to triangle XBA. All right. And then we could show AY over YC is DX over XA. So that shows that those whole triangles have to be similar, which solves the problem basically. I feel like, yeah, it really is that
Excuse me,
simple.
sir.
So,
Can I say something about
yeah, sure.
if we define D as the intersection of B, K, and AX, then forgetting that CHD are collinear, then CHD turn out to be collinear by Pascal's theorem on the hexagon in the circle.
Interesting. So you're saying if we didn't know this line exists, we could use Pascal's theorem to show CH and D are collinear?
Directly follows.
So did you define, basically, did you define K to be where YE meets the circle, and then use Pascal's theorem to show CH and D are collinear?
Yes.
Ah, interesting. Maybe I could show all this. Maybe I could show both solutions. So first I'm going to show my solution, and then I might type. I think I'll type up that one. So what was I going to say? So yeah, we have. So yeah, I'm going to write out the parallelism. So XF is perpendicular to BY, means that XF is parallel to AC. And then similarly, YE is parallel to AD. And so that means that dx over xa is equal to dh over hc, which is equal to ay over yc. And so so we use both these parallelisms here, and from there it follows that since we knew YBC was similar to XBA, then it follows that ABC has to be similar to BBA. So whoops. And if that's true, then angle BBA equals angle ABC. And so BA bisects angle ABC, angle CBE. All right, so that's proof one. Now I'm going to try to do Anmol's suggestion. Let's do proof two. Does this make sense to everyone? Just assume it does. All right. So now I'm going to delete this and try Anmol's idea. So Anmol says, let K be the intersection of BD, or I'm trying to remember. So let K be the intersection of YE with the circle, and let BK intersect AX at D. And then you said you can use Pascal's theorem to show DH and C are collinear.
We are missing a fact here that we did not prove earlier that Xi, HF are collinear.
Oh yeah, so
We need to prove this to finish off with Pascal theorem.
but yeah, it's not hard to show X, HF, and I are collinear because since AX BI is I mean, since AX BI is
Yeah, they are all under some cyclic quadrantals or something like that.
yeah, so angle AIB is 180 minus angle AXB, so it has to be 90 degrees, right? So that it's not too hard to show that. So once we know that, do you see how to use Pascal's theorem? Let's see. So we would be using Pascal's on A, Y, I, B, X, A. So A is twice. So it would be AA, YI, BX.
No, there is a point K also, so I think it should be AYIBKX.
AYIBKX. Okay. I think you're right. So AX and BK, XI and YK, and AY and BI. Okay. So that's proof two. Yeah, I skipped a bunch of stuff, but yeah, let me I'll first say what you mentioned. So let me hide this segment. So the reflection of H over F lies on the circle BXY. And also, I'll say the reflection H prime, or the reflection H prime. And then whatever that point is, angle AH prime B is 180 minus angle AXB, which is 90. And so X prime equals I is the foot of the perpendicular from A to BC. Sorry, H prime equals I. And so we can draw that in. And then we can apply Pascal's theorem, and we get that C, H, and D are collinear. So yeah, I didn't write that I redefined, so I'll just write that just to be picky. So we're redefining A is the intersection of YE and the circle ABI. And we're redefining D as BK intersect AX. Yeah. And so then we apply Pascal's theorem, and those are collinear. But then it's easy to see from here that I'm just thinking the best way to write it out, but basically YK is parallel to AX. So arc AY is equal to arc XK. And so that means angle KBX is equal to angle YBA. All right. And then as in the previous proof, we have angle CBY is equal to angle ABX, because I'll just write it out quickly. Oops. So adding the two, gets us what we want. So angle EBA equal to angle ABC, and that's all good. So I'm kind of wondering here, I use that YH is parallel to AB. Did I use that IX? Oh yeah, I did. I used that the reflection of X over BY lies on the circle, which is this point I. Okay, so yeah, I used all the information. Yeah, thanks for that proof, Anmal. And yeah, I3435, if you want, you could post the idea you had on Discord. All right, so I'm going to move to the next one. So ABC is a triangle with circle omega. Hold on just a sec. Yeah, sorry I didn't tech these up. The bisectors of ABC and ACB intersected at, obviously it intersected at the midpoint of those arcs. Which they call X and Y. K is on CX, such that KAC is 90 degrees. Okay, so we're going to want to, let me erase it for just a sec. We want KAC is 90 degrees, and LAB is 90 degrees. Okay, so I want to shrink it a little bit. So this is point K. And LAB is 90, but that's on BY. Okay, this is L. Looks kind of familiar, I feel like. S is the midpoint of arc CAB. So this is S, and we want to show SK is equal to S now. All right, so I'm going to hide some stuff here. Let's see. Draw that. Draw. Let's see. Draw this, and then this, and that, and then hide everything else. One of you has some background noise. Oh, hey, Enrique.
Oops, sorry. Hey.
Oh, it's all right. Hey, thanks for joining. All right, we got a good group here. So we want to show SK is equal to SL. Feels like there's probably some congruent triangles somewhere. So maybe, I wonder if angle LSB plus angle KSC is 180. Let's see. I'm going to test that out. LSB is 55, KSC is 124. Yep, they add up to 180. All right, so it's kind of like, so what made me think of that? It's like if we want to show SL is equal to SK, but we know SB is equal to SC. It's kind of like when we fuse those two triangles together, SLB and SKC, it's like we would get, like we'd be able to fuse them together basically, because since these angles add up to 180 and SK, if it were true that SK is equal to SL, then we could connect. I don't know if you guys kind of see what I'm saying, but like if we extended CK to a point so that KJ, let's say, is equal to BL. Oh no, I'm sorry. If we extended CS to a point J such that SJ is equal to BL, then JKS would be congruent to triangle BLS. So maybe I'll do that. It'll take a little more space, so I'll have to maybe minimize the figure a little bit. But what if I did that? Wait a sec. Yeah, basically, we want to show that triangle SKD is congruent to SLB. Where S is the center of this circle. Yeah, I don't know if that makes it harder, maybe. Did I set that up right? Hi, Ira John. Yeah, so I don't know if, thanks for joining, Ira John. Yeah, with daylight savings time, everything's like, so in the US, we do something where we set our clocks back an hour at a certain point in every year in the spring. And so that's why it's like an hour difference. So from now on, it's it might start an hour earlier for you. But yeah, we started an hour ago. So hold on just a sec. So Anmol says KLSA is cyclic. All right. So yeah, maybe I just complicated the question by adding this. KLSA is cyclic. I'm guessing that's probably an angle chase. Let's see.
Maybe this is just a conjecture I saw, but we can try to see if this cyclicity proves the problem.
Okay. I think it might, because let's see, we want to show SK is equal to SL. That's the same as showing angle, of saying angle LAS is equal to angle ASK. I think it would solve the problem. I think there would be an angle chase that could get you to solving the problem. So yeah, if we can show that's cyclic, I think it might get us there. Let's see. Are triangles LSB and KAC similar? Let's check it out. So LSB and AKC. No, they're not similar. It's pretty close, but all right.
This S turns out to be the circumcenter of I, L, and K. I is the incenter of ABC.
Yeah, that would probably be a good idea to draw the incenter. So, did you say ILK? Is A the incenter of ILK?
No, I am saying that we need to prove that S is the incenter of ELK.
Oh, I don't think S is the incenter of ELK.
I think you can try drawing it.
So like, I guess like, so in this figure, like, I'll change it to I just to be the incenter, but like, I guess at least in this figure, S doesn't look like the incenter of ILK, right?
No, it is the circumcenter.
Oh, the circumcenter,
I mean
sorry, my bad. I misheard you. So S is the circumcenter.
It is indeed.
Oh, that's interesting. That would solve the problem. Let's see. Let me delete some of the extra stuff I drew. Just to make it easier. Y is the midpoint of BL. Oh yeah, Y is the midpoint of BL because YA is equal to YB. Yeah, okay. So I think this is probably, yeah, we use the in-center, x-center lemma. So YB is equal to YA. Yeah, so we know LAIB is cyclic, and we also know KAIC is cyclic. We don't know that one yet, but maybe we could prove it. Maybe that's like probably just an angle chase, I would bet. Yeah, let me make this diagram a little nicer. So, okay. So yeah, can we use that to show that LASK is cyclic? And then that would probably solve the problem. It's probably, let's see. I don't want to make LA and C look collinear. It's hard to make LAC not look collinear, but we'll just have to keep that in mind. So, yeah, I think we could probably show angle LAK. I was going to say LAK equals LSK, but now I'm not sure that's so obvious. Let's see. So LIX is 90. KIY is 90. Yeah, we just want to show LASK is cyclic. Let's see. I'm sorry. Can we prove that SY is the bisector of IYL? Hold on. But first, I'm looking through Irajon's suggestion, and then I will look at Enrique's suggestion. So, if Y is the mid, is that true that SY is parallel to XB? It looks true. Okay, so if we could show arc BY is equal to arc SX, that would prove it. And that shouldn't be a difficult calculation because arc BY is half of arc AB, and arc XS is arc BAC. Okay, let's say I could prove YS is parallel.
All this seems like that again LAIV is cyclic and Y is the circumcenter. Similar going from other side proves that LASK is cyclic.
Say that one more time. So y is the circumcenter of LAIB, right? So arc BY equals AY equals SX equals XC. Or arc BY doesn't equal XC, but our arc BY equals SX. So hold on just a sec. Yeah, so so how would that, so once I show that SY is the bisector of IYL, how, oh, that would show that S is this, oh, okay, yeah, okay, so I think we've solved it. Okay, so I'm gonna write it the solution. Yeah, Enrique's idea is interesting. But like if I label this other point, I think that might also work, but for now I'm just going to stick with the solution. Okay, so let me delete a couple things I added. I added that circle, and I'm going to add it back in throughout the proof. Okay. I think I could probably move the diagram far enough where I could see the text. So by the in-center, x-center lemma, we have yi equals yb equals ya. And then since angle LIB is 90, that means that in fact y is the circumcenter, or I'll just write it like this. Yi equals YB equals YL is equal to YA. So that means LAIB is cyclic with circumcenter Y. All right. And then similarly, KAIB is cyclic. I don't even know if we need that they're cyclic actually, but we'll just write it out for now. All right. We'll draw those two circles. Sorry. Now I want to show that ys is parallel to dx. And once I do that, that's the same as showing that basically S lies on the perpendicular bisector of IL. And then I would use the same argument to show that S lies on the perpendicular bisector of IK. And so that would mean S is the circumcenter of it, which would solve the problem. Okay, so so arc BY is half of arc AB, and arc SX is arc SC minus arc XC. So yeah, I'm going to write it out like this. So arc SX is equal to arc SC minus arc XC, which is equal to so SC is half of AB plus AC. Okay. And XC is half of AC. So this is half of arc AB, which is arc BY. Okay. And so that means that SY is parallel to BX. And then Y, since Y is the midpoint of LB, that means, so SY is parallel to BX. I'll just say that means that SY is perpendicular to LI. And then, since LY equals YB, then SY is the perpendicular bisector of LI. And similarly, SX is the perpendicular bisector of KI. So that means S is the since S lies on these two perpendicular bisectors, S is the circumcenter of LKI. And so that means SK is equal to SL. All right, sounds good. All right, let's move on to the next one. This is a fun one. Another 2020 Baltic Way. There's 20 problems on each Baltic Way because it's a team contest. So AB is greater than AC in this case. The internal bisector BAC, it intersects BC at B. The circles with diameters BD and CD is interesting. So we draw the circles with diameter BD and CD, and we see where they meet the circumcircle of ABC. All right, so I am going to hide that line. It's hard to see the intersections here. Let's see. How do I draw it so that looks a little better? I want like a tall triangle. And then P and Q. And then we want the intersection of PQ with DC. All right. Let's see how it goes. I don't want them to intersect really, really far away. Maybe that works. they intersect at x, and we want to show that AX is tangent to the circumcircle of ABC. It's a pretty cool problem. All right. So obviously that would mean XA squared is equal to XC times XB, which is equal to XQ times XP. What if maybe there's like a way to use the radical axis theorem? So we have the circumcircle of ABC. We could try like the point circle A, I'm wondering. Is BC PQ cyclic? Yeah, because they're defined to all lie on the same circle, B, C, Q, and P, so they have to be cyclic. Is XA equal to XD? It's all good. Could be. Yes, XA is XD. So maybe some polar, like, just thinking. So X, we want to show XD squared is XC times XB. Yeah, I should draw an angle bisector. So I've kind of just left that out. Now by power of a point, DPQ is tangent to BC. If we know that, yeah, if we prove XA equals XD, that would be the same as showing a tangent. And I would guess it's probably not an easy, I'm sorry, not a hard angle chase to show their tangent. So let's see. Because we want to show that. So we have that 90 minus that, which is 90 plus that, which, yeah, so I can prove that I can prove it's tangent through an angle chase. Yeah, the question is how. Okay, so yeah, 8XD squared is XQ times XP, which is XC times XD, XC times XB. And yeah, does an angle chase show that XAD is? Let's see. Yeah, maybe it's some radical axis theorem. Let's see. And then XD squared is XB times XC. How does that follow? So I agree XD squared is XB times XC. But then oh, it's let's see. Okay, so yeah, we're using harmonics here. Okay. I think I've seen this idea before. Yeah. I'm just thinking it through in my head, but no, it sounds like you have like that works. Hold on just a sec. All right, so I'm gonna start typing this up. Whoops. Okay, so I'm gonna delete that for now. Yeah, eventually I'm gonna have to move the diagram a little bit, but for now, we have how did I do that? So angle DQP is equal to angle PQC minus angle DQC, which is angle PQC minus 90, which is 180 minus angle PBC minus 90, which is 90 minus angle PBC, which is angle PDB. See if that fits. Let me break it up into two lines. Whoops, that didn't work. How do I break this up? See if that works. Tricky. I'll figure it out eventually. Do two, what? Come on. All right, I'll just do this. Just two separate statements. No, the copy went away. Oh, no, there we go. All right. So BC is tangent to the circle DQP. All right. So we can now draw that in, because if angle DQP is equal to angle PDB, then yeah, it's tangent. Let's see what we have in the chat. We can also use phantom points. Interesting. Okay, so that means that XP times XQ, or I'll write it out like this. So we have XB times XC, why not? Q, which is equal to XD squared. And that should be enough, because now what we can do, and here's where we use that angle bisector fact, which we haven't used yet. Well, let's see if I can get enough room in the diagram here. Shrink this figure. Oops. What am I doing? I have to move both. Let's see. This doesn't look so bad. I can do something like this. Okay. So basically, here's where we use the projective geometry. Let me just move everything over. So I'll say draw G on these X, or such that angle DAG 90 degrees. Then it's well known that B, C, D, and G are in harmonic conjugation. So I've done this on my channel before, so see my second video on projective geometry. And so that means, let's see, so we have XB times XC is XD squared. Yeah, so I'm trying to think, how does it follow from, I know I've seen this before, I'm just trying to remember it. How does it follow from XB times XC is equal to XD squared, that X is the midpoint of BG? I've seen this fact before. Is there like a fast way to see it without algebra bashing? Let me check the chat again. Is there a is there a quicker way to show that X is the midpoint of BG that's not algebraic, but let's think. So
maybe the fact that the harmonic implies that GD and BC are like on orthogonal circles, and X should be kind of like, wait, yeah, like the circle with diameter GD is orthogonal to to the circle with, no, wait, I think I'm getting confused. Never mind.
I think I feel like I've seen what you're saying before. So if you draw the circle with diameter DG and the circle with diameter BC, maybe. Let me try.
Yeah, but that wouldn't tell us. Like, if you take the circle with diameter BC, that wouldn't tell us about the tangency.
So yeah, I think it's a well-known fact. I feel like I've seen this before, that if XB times XC is XB squared, then X is the midpoint of DG, where G is the point that makes a harmonic conjugation. But yeah, there must be a geometric way to see that. Or I would think at least. So yeah, like, and I guess if we let like a prime be the tangent from x to the circle, then xd is equal to xa prime. We want to show a and a prime are the same point. Let's see. Let x prime be the intersection of BC and the A tangent. Okay.
Is EFPQ cyclic?
Is EFPQ? Let's check. Where's my circle? No, but it's close. Let me see Irijon's way. Let x prime be the intersection of BC and the A tangent. ABC and PDQ. I'm trying to understand. Okay. Hold on just a sec. Okay, I think I have an idea here. Okay, I think Irijon kind of, so yeah, I think, okay. All right, so what I'm gonna do, I'm gonna get rid of point G temporarily. I'm gonna get rid of point G. I'm gonna think about it a different way. So we have this equation right here. Now it turns out the tangent at A to BC, if you draw it in, it's not hard to show that if it meets BC at a point x prime, it's not hard to show that x prime AD is isosceles by an angle chase. So I think, yeah, that should do it. Okay, so basically, if we hide a bunch of stuff, So what I'm going to do is I'm going to say, I'm going to let x prime be the intersection of the tangent at A to BC. So thanks for this idea, Ira John. And then by an angle chase, we can show x prime AB as isosceles. So yeah, so we have angle x prime AD is equal to angle x prime AC plus angle CAD, which is equal to angle ABC plus angle BAD, which is equal to angle ADX prime. I like this. And so that means that x prime A is equal to x prime D. And we also have x prime A squared as x prime C times x prime B. Or I'll write this, x prime D squared is equal to. Okay, so basically, there's like some trivial algebra here, but if we had xb times xc was xd squared, and now we have x prime b times x prime c is equal to x prime d squared, then x has to equal x prime. So I'll just write it like this. X prime is equal to x. Leaving out a couple steps there, but it's right. It's not hard to show that there can only be one point where xb times xc is equal to xd squared, right? All right, CI345. Thanks for joining. And so I will connect those, and now we can call that x. I'll just leave it as x prime, why not? And so therefore AX is tangent to a certain circle. So yeah, this is a fun one. I like Ira John's way of proving this. All right, so now I'm going to move on to the next one.